And in order to do that, we will take a step back and ask ourselves, why are we doing all these things? Why are we dealing with latent variable models? And what is so cool about this posterior distribution, and in particular, what is so cool about these posterior distributions that are hard to get? Okay? And to understand this, we will look again at latent variables. And when you look at unsupervised learning literature, these latent variables Z are very often interpreted as kind of the quintessential information that is present in the data. Okay, so that's the quintessential information that you can compress your data to. And that's, of course, why this posterior distribution all of a sudden gets the holy grail of many areas in machine learning. Because if you know the posterior, if you can compress it to the quintessential information, you can throw away your data and you have all the intelligence or the learning drawn from the data that you could. Okay? And actually, if you look at this posterior distribution closely, if you replace the latent variables again with labels, and you look at supervised learning techniques, you can see that a lot of supervised learning techniques actually try to learn this posterior distribution, but simply try to learn it from labeled data. Okay? And we saw that the EM algorithm can solve or can learn the posterior distribution in an unsupervised fashion, but the problem is we explicitly needed the posterior for a given parameter set, theta. Otherwise, the E-step wouldn't work quite as we had planned it to do. We couldn't update these responsibilities so well. Okay, but why is this problem so hard? And that boils down to the question, what is so hard about this posterior distribution? And to see that, we are going to have a look at it again. So here's the posterior distribution, and we decompose it into this generative model and the data log likelihood. And the generative model is typically at least easy to formulate. You have to specify your latent factors, and then you have to specify how they influence the observables, the images, for example, in the MNIST case, and then you just have to say how are these latent factors distributed. That's typically the fairly easy case, and that's why the graphical model had the direction we saw on one of the previous slides and not the other direction. What is much harder is the data likelihood. That's what we were struggling with from the beginning. And that's because we have to solve this integral, and this integral is typically very hard to solve. Now, if you remember our example, it was actually not so hard to solve this integral. It was just a summation over these components, and it was fairly easy to marginalize Z. Well, the reason is that the Z we had for our digits was very simple. The Z was really just the digit, but I already hinted that there are many more latent factors that we didn't take into account. So for example, there would have been rotation, there would have been skewness, the absolute position of the digit on the canvas. All these things were not incorporated in our latent variables. And that is what made the integral fairly easy. We had a lot of information in the latents, but not all the information that is present in the pixels. And if we had included all these things like rotation and skewness, this integral up here in the denominator would have gotten harder and harder and harder to solve, and at some point we wouldn't have been able to solve it anymore. So that's a problem. And there's another problem. Even if you were able to add all these latent factors like rotation and skewness, you really wouldn't want to do this because you have to hard code a lot of structure by hand, and you have to really put a lot of thought in how they actually affect the image and so on and so forth, and that's very hard to do. And when you're used to neural networks, a very natural choice is to say, okay, I don't want to hard code this thing, but it's a function and I can approximate this function, and why should I not just use a neural network for this distribution, this generative distribution, which is also this distribution up here in the numerator. So you don't want to specify by hand how the latents influence the observables, but you just want to say it's a function, and this function is approximated by a neural network. So when we consider neural networks, we can definitely conclude that the posterior is very hard to obtain. And for a lot of models that are more sophisticated than a Gaussian mixture model, it's really hard to get this posterior. But now we can remember something from our analysis of the EM algorithm. When we analyzed the E step, that is the update of the responsibilities, we found that we were explicitly doing the left-hand side of this equation, that is the minimization of a KL. And we could do this because this posterior distribution was available to us, okay? And because it was available to us, the solution for Q was trivial. It was just the posterior. And we could just evaluate the posterior and update the responsibilities. And in the analysis, the theoretical analysis, we showed that this was actually equivalent to the coordinate descent in Q of the evidence lower bound. Now, if the posterior is not available, like it is for a lot of interesting models, we cannot at all do the left-hand side, and that's a problem. But now we can flip this duality, and instead of implicitly doing the right-hand side, the maximization of the evidence lower bound, we can just explicitly do it and then argue if we explicitly maximize the evidence lower bound, we're implicitly missing the minimizing the KL divergence. And that's quite an amazing thing. We cannot tell how well Q approximates the true posterior because we don't know the true posterior. But we know that if we seek a Q that maximizes a completely different objective function, this evidence lower bound, we will still find the one approximate posterior Q that approximates the true posterior in the optimal fashion. Okay, now that's a nice way of trying it, but the question now is, the left-hand side is not doable, but the question really is the right-hand side doable? Okay, let's look at the right-hand side. Let's look a little closer at the evidence lower bound. By definition, the evidence lower bound is this integral. It looks a little bit like a KL divergence, except that these two are flipped. And the much bigger problem is that this one depends on x. So it's not really a KL divergence. But this already hints at the direction we're going to take to simplify this expression. Namely, we're going to split up the joint model into the part that depends on x and the part that depends on z. And from here on, it's fairly straightforward to apply the logarithm rules and end up with this expression that consists of a KL divergence and a different expectation. Namely, it's the expectation of this generative model that states how z influences x, and that was just our neural networks. So we have our hands on this one. We also have our hands on Q naturally, because that's the thing we're optimizing for. And we just need to choose a prior, and that's up to us what we want to choose here. And this means both of these two terms, both this expectation and this KL divergence, do not require this posterior distribution. And that's even more amazing. By this duality up here, we can maximize the evidence lower bound, and we will get the optimal approximation to the true posterior, even though we don't know it. And now we analyzed it a little further, and we saw that the evidence lower bound doesn't even require this posterior. That is, we can find, with the help of the evidence lower bound, the best approximation to the posterior distribution that we so desperately want to find. So there is one little issue that we haven't addressed yet. When we are looking for an approximation of the posterior distribution, we need to find a set of functions where it's very likely that there's a good approximation in there of the posterior distribution. The problem is we don't really know the posterior distribution, and that is particularly the case when this forward distribution, this generative distribution that tells us how z influences x, is implemented by a neural network. Okay, so what we need is a set for Q of parameterized, that is learnable functions, and they should cover a range of functions as wide as possible in order to maximize our chances of actually getting a decent approximation of the posterior distribution. Now, if you think about these requirements for a while, there's quite an obvious choice actually, namely to just pick neural networks. If this distribution up here can be implemented by a neural network, we can also implement our oracle queue by a neural network. And how does this look like in practice? Well, in practice, you have a neural network which takes X as input. So this is the neural network. And as output, you get, and it's parameterized by the parameters phi, which is distinct from theta. And it outputs a mean, and it also outputs a covariance matrix. And then you sample Z from this distribution according to these parameters. Okay. Now, the difference to a standard Gaussian distribution is that these parameters mu and sigma can highly nonlinearly depend on the input, depend on the observables. And that's what makes this distribution so flexible. And actually, the way this is implemented, when I say this is implemented by a neural network, is also exactly this way. It's just reversed. You insert the Z, and the output of the neural network are the parameters of, for example, a Gaussian distribution, or whatever distribution you want to have. So in our analysis of the EM algorithm, we concluded that it's probably not such a good idea to always hard code the structure that is present in our data, like the skewness, the rotation, the digits, because it just gets out of hand and it's too hard to model. So we decided to use the flexibility and approximation capability of neural networks, and we decided that the neural network should decide how to map the latents on to the observables, and should do this in a probabilistic fashion. And in order to avoid this hard coding, we now also need a second mapping, which maps the observables in our dataset, like the images of the digits, onto the latents. And this is called a recognition model because it recognizes the latents or the presumed latents from the observables. And in order to match the capabilities of the first neural network, we decided that it's probably a good idea to also use a neural network for this mapping. So we have two neural networks that work in opposite directions. So one maps into the latent space. It's kind of an encoder. It encodes the data in the latent space. And then there's the decoder, which maps back to the observables. So you have some kind of autoencoding mechanism. And now we also found that there's this intriguing error function, namely the evidence lower bound. And we found that it jointly maximizes the generative model and also this approximate posterior. And because we decided that the approximate posterior is a neural network parameterized by the parameters phi, we can redefine the evidence lower bound in terms of these two sets of parameters. And it keeps all its intriguing properties, and we can jointly train both of these neural networks with one very, very nice error function. And if you put together all these parts, what you get out is the so-called variational autoencoder. So the autoencoding part is exactly what I was talking about, this decoding distribution and the encoding distribution. That's kind of like the classical autoencoder. And the variational comes from the fact that, again, we're optimizing over functions and not just parameters. And these are fairly recent findings, end of 2013, beginning of 2014, two individual papers that both discovered that you could do this. And they were very well received in the community and have spawned a lot of research. And these two last bullets down there are actually links. So if you want to look at the original papers and see how they explain their methodology, you can just follow these links and they will guide you to the papers. Now, we're almost done with this lecture, and I would like to use the remaining slides to convince you why the variational autoencoder was so well received within the research community. And to do that, I'm going to compare it to a deterministic autoencoder. And you may remember the deterministic autoencoder from the neural network lecture. What it did was it took an input data point X, took this encoding mapping F, generated a latent code Z, which is fully deterministic depending on X, and then decoded this code Z with a function G into an estimate of the original data point. Sorry, that's not F, but G. And then what you typically do to train this is you try to minimize the distance between the original data point and this new estimate X hat. And what you want to do is you want to prevent this neural network to just learn the identity. Because you want to use these latent codes Z later because you think that they will hold more condensed, more compact information than the actual input. And to do that, what you do is a dimensionality reduction in the latent dimension. So Z has a lower dimension than X, and that is supposed to force this autoencoder to compress the information. And on top of that, you typically have regularizers on the weights of the neural networks and so on to prevent overfitting to the data set and all these issues. In practice, it turns out that this doesn't help enough. Training an autoencoder is typically very unstable. But I will argue now that the variational autoencoder does a very similar thing, except that it's more principled. And this more principled fashion of approaching this autoencoding mechanism also greatly improves the training procedure, which is why it was so well received. Okay, so what does the variational autoencoder do differently than the autoencoder? The variational autoencoder also has a bottleneck, but it does not come from dimensionality reduction like in the autoencoder case. Instead, we employ a stochastic layer here. Okay, so instead of having a deterministic Z, we draw a random sample from this distribution that is the output of the upper encoding neural network. Okay. Now, I would argue that this is in some way very similar to dimensionality reduction. Why is that? Well, let's look at two data points. We have two data points, x1 and x2, and they're distinct. And now we will look at their approximate posterior distributions. The one for x1 looks like this. So this is the posterior distribution given x1. And this is a sketch of the posterior distribution given x2. Okay, what do we observe? The most important thing we observe is that in this area here, these two distributions overlap. And why is this so significant? Well, after all, we're trying to decode again. We're trying to get back our original sample, our original data point x1 or x2. Now, because we're sampling Z in this red box here, and Z comes from either one of these two distributions, both distributions might come up with this point here in the middle. Both share probability mass there, so it's a valid sample for both of these distributions. But now the second neural network, the decoding neural network, has a problem. It has to figure out from this Z whether it came from x1 or whether it came from x2. But it can't do that because it's probable that it belongs to both of them. Now, what this will force the learning algorithm to do is to learn to put these two bumps apart. So it will try to place these Gaussian bell curves on this real line such that they share as little support as possible. But that also implies that there is finite space to store information because you can't just reserve a single point for the latent code like the deterministic autoencoder did. The deterministic autoencoder mapped x onto one specific z, but you have to reserve a bandwidth for this latent code, or this latent distribution rather, so that you can identify the original data point again. And that's why you have an information bottleneck there. You can't store infinitely much information, even though you have the infinitely large real line there. Okay, and this can also be seen when you look at the actual error function, the evidence lower bound. Okay, so let's look at it. Let's look at the two terms individually. Let's look at this first term. If you look at this distribution inside the logarithm, and if you remember the old slides, you will see that this is a Gaussian distribution here. This is a Gaussian distribution with a parameter mu that depends on the neural network parameters and the input z, and similarly the sigma depends on the neural network and the input z, but it's a Gaussian distribution. And if you take the logarithm of a Gaussian distribution, what you essentially get is a squared error between this data sample x and the mean of this Gaussian distribution. So you have exactly this squared error that you would probably use in the deterministic autoencoder too. And the expectation over QZ is simply solved by sampling. So you have a Monte Carlo sampling of this expectation, and you just have a one-shot sampling, which is essentially this squared error. Okay, so this is another similarity to the deterministic autoencoder. And now you have this second thing here. If you listen closely in this analysis of these bell curves that are drawn apart, you might have also argued that, well, why doesn't it just reduce the variance? That's a very fair point. It can actually reduce the variance, and then it again has infinite space for information in the latent space. But then you have this KL divergence, which tells you that this evidence lower bound punishes you if you deviate too much from the prior with your posterior. So you set this to a prior that is typically, for example, a non-informative, or non-informative is the wrong term, but not very informative standard Gaussian distribution, and deviations from this standard Gaussian distribution in your approximate posterior are punished by this KL divergence. And that in particular means you cannot reduce the variance to zero, because if you do that, then the punishment approaches infinity. So what this KL divergence here does, is that it serves as a regularization. And the nice thing is, if you use Gaussians, this can be solved in closed form. And it also enforces some kind of spatial coherence. So it enforces that your latent space is organized where the standard normal distribution has support. It can't just store the information anywhere on the real line or in R2 or RD, but it has to be where the normal distribution has mass. And that's a very strong regularizer. But the very nice thing is it very, very naturally falls out of this evidence lower bound. So we don't have to come up with it. We don't have to fit any hyperparameters. There's no lambda here that we have to set. Just forget about this lambda. We don't want to set this. It's very tedious. And that's a very, very nice property, again, of this evidence lower bound. So to summarize, the variational autoencoder, along with its error function, the evidence lower bound, rewards good reconstruction, just like the autoencoder did. And it comes with a very strong, very natural inbuilt regularizer that prevents it from collapsing to the deterministic autoencoder, because the deterministic autoencoder does exactly this thing, that it reduces the variance up here to 0. And that is what makes it much more stable and much more popular these days than the deterministic autoencoder. So hopefully I was able to convince you that the variational autoencoder does something very reasonable, very nice, and that it improves upon the deterministic autoencoder in a very natural and very well-behaved fashion. What I didn't mention is a very big obstacle when you're actually trying to implement this thing. And it's one of the big issues tackled in these two papers that I mentioned earlier. Now, the problem is that we have to do backpropagation, that is taking derivatives through a random sampling process. Remember that in this middle layer of the variational autoencoder, we're drawing a random sample. And we have to do backpropagation there. And first of all, let's try to understand what the problem is. Okay, so we're trying to take the derivative with respect to the recognition model parameters of an expectation that depends on a distribution, which in turn depends on the parameters we're trying to take the derivative of. Okay, and the argument is a function. It doesn't really matter which function it is. In our case, it's a log likelihood. The really important thing is that it does not depend on phi. Okay, now let's spell this out. If you look at this is an integral, and now we can pull in the derivative, the gradient, and we take the gradient with respect to this distribution. Sorry, that's the wrong parameter. Don't mix this up. Okay. So we pulled in the derivative, and at first glance it doesn't look too bad because this is unchanged and we know this thing. And this is a neural network, and we're taking a derivative with respect to its parameters. That's also doable. That's the normal backpropagation algorithm. Well, that's fine. The big problem is we still have to take this integral. And we have no idea what this integral is, especially after taking the derivative. Before taking the derivative, this was a distribution, this Q. So this was an expectation, and expectations are easier to handle than general integrals. But this derivative destroyed this distribution and this expectation, and now we can't backpropagate through this integral anymore. Okay, but the people who wrote these original papers, Kingma and Welling, and Resende and Mohammed, they found a very nice solution to that. Okay, they looked at how do we typically sample random variables. For example, if we have a Gaussian random variable, we don't directly sample it, but we sample from a standard normal distribution first, because that's easier. There are pre-written or predefined algorithms for that. We sample an epsilon. And then we do a affine linear transformation. So we scale this sample epsilon by L, and L is kind of the square root of the covariance. So remember maybe the Koleski decomposition. And then we also add the mean. And if we do this affine transformation, we know that this transformed random variable follows this mu sigma Gaussian distribution. Okay. Now, how is this relevant? Well, instead of saying z sampled from Q of z, we change this into epsilon sampled from a standard normal distribution, and we insert this kind of from the side, and then z is just a function that takes two arguments. It takes epsilon, and it takes the parameters mu and L. Okay? And now this upper neural network, its job is to output mu and L, and when we want to take the backprop algorithm, we want to take the derivative bottom up, And all we need is the partial derivative with respect to these parameters mu and L, and the epsilon is completely irrelevant for taking the derivative. And that's a very nice way to sidestep this problem. We just reformulate our backpropagation, and we can suddenly take the derivative. And that's one of the key findings of these papers. Two more things to mention on this slide. This way of sampling is one more reason why you should prefer, or why people like to use the Gaussian distribution, because it's very simple to implement the sampling process for the Gaussian distribution and to do all these backpropagation steps. Now, another thing is there is another solution to this derivative problem, okay? And this trick has been known for a long time, but I will soon tell you why it cannot be applied here, or it can be applied, but why it shouldn't be applied. And the trick here is that in order to take the derivative of this q phi, sorry, this is now a slight abuse of notation, to abbreviate this a little bit. Right now I'm claiming that this is the same as taking the derivative of the log likelihood of the very same distribution and then multiplying this with the original distribution. Okay? And to see why this is the case, simply take the derivative of the log likelihood, and you will see that this is actually equal to 1 over q times the gradient of q. That's the derivative of the log likelihood. And then this 1 over q cancels out with this q, and you're left with the gradient of q, and that's the left-hand side. Okay, so that's a small trick, but if you look at it closely, the left-hand side is actually this problematic derivative up there in the integral. And now you can replace it with this different term, and all of a sudden you have this q again. Okay, you have another term, you have this derivative. It's a bit of the log likelihood. It's a bit nasty, but you can calculate it. And again, you get an expectation, okay? You have an integral over a distribution, so this integral is again an expectation, and you can solve it, for example, by Monte Carlo estimation. Now, this trick has been around for quite a while now. One problem with it is that if you do Monte Carlo estimation of it, that is, you take one sample and say, okay, if I evaluate it at this sample, this is approximately equal to the true value, then this has an extremely high variance. So high that the gradients get so noisy and so bad that you cannot train your models on this. And this is true in almost all scenarios that are relevant for us, like in the variational autoencoder. It's not true for all cases. If you're interested in when it's not the case, you should look at this guy's fairly recent PhD thesis. He analyzed this problem and showed that in most cases this log derivative trick is not applicable, but it's still a very handy and very nice trick to keep in mind.